So we're facing an integral of a rational function, which moreover is an improper integral. So first of all, let's check the points at which this integral is improper. For sure, infinity is one of them. But we should also be careful about the denominator. And so let's factor this. So it's x times x squared plus 1, which is 0 only at x equals 0, and that's not within this interval, so this is improper only at infinity. Therefore, we have to interpret it through a limit. That's the definition of an improper integral. So introduce a parameter t, that's the limit as t goes to infinity, integral from 1 to t of the function. Now let's just worry about computing the indefinite integral first, and then we're gonna take the limit later. So again, here we don't really see any sort of pattern or any easy substitution that we could make. So let's just jump ahead and do partial fractions decomposition. So we notice that we have a linear term x, which is not repeated, so that we'll get just a constant a on top of it. And then we have this one, which is a quadratic term, which cannot be reduced anymore. So this gets a linear term on top of it, of the form bx plus c. So we look for the decomposition of the following form. Now we just need to find the coefficients, a, b, and c. Multiply both sides by this denominator, so we can simplify it here. And we get it in there. So this side is x squared plus x plus 1. And here, when I hit this with this product, I simplify in x, and I'm left with x squared plus 1, multiplying a. And then when I hit this term, I'm just left with an x, multiplying this bx plus c. And then multiply this out. We get ax squared plus a plus bx squared plus cx. These are the terms in x squared. So a plus b times x squared. Then I have only one term in x, which is c, x. And then I have the constant term, which is a. And this must be equal to this polynomial. So I get a system of three equations in three unknowns by setting these coefficients to be equal to each other. So here the coefficient of x squared is 1. So a plus b must be equal to 1. Here. Then c, which is the coefficient of x, must be equal to the coefficient of x here, which is again 1. So c equals 1. And then a has to be equal to the constant term, which is again 1. So that's our system that's already pretty much solved, right? We just need to find b. That's 1 minus a. So that's 0. And therefore we have our partial fractions decomposition by putting those coefficients in here. So this indefinite integral becomes the integral of these two. Now a is 1, so I can put it in here. And b is 0, so I don't have it. And c is 1. So those are these simpler fractions that we are going to integrate. 1 over x is a logarithm. And 1 over x squared plus 1 is arctangent plus c. That's the indefinite integral. now our problem was this improper integral. So once we have an antiderivative, we need to evaluate at the endpoints t and 1. So I'll get rid of this. And I'll continue the calculation here. Remember to always write limit when you're computing the limit. So first you plug in t, you get ln of t plus arctangent of t, and then you have evaluated 1, so you have ln of 1 and arctangent of 1. So ln of 1 is 0, so this is not here anymore, and arctangent of 1 is pi over 4. But those terms do not depend on t, so the limit is actually here. We need to remember the limits of these elementary functions. So arctangent as a horizontal asymptote, so approaches pi over 2 when t goes to infinity, but the logarithm approaches infinity. So this limit is positive infinity, meaning our improper integral is divergent. So just as a reminder, this is the graph of arctangent. There's two horizontal asymptotes, y equals pi over 2 at positive infinity and y equals negative pi over 2 at negative infinity, while logarithm is like this. So at positive infinity it goes to positive infinity, and when x goes to 0 plus it goes to negative infinity.